first of all, I'd like to thank the organizers for giving me the opportunity to talk here. As Marek said, I'll be talking about a very peculiar idea of adding a single neuron to a complete neural network and doing it in a way that hopefully helps the network do what it's supposed to do. I'll be focusing more on the mathematical side of loss functions and neural networks in general. So hopefully you find that interesting. First of all, I need to talk a little bit about loss functions in general. Then I'm gonna, give you a very brief definition of the task at hand. And then hopefully I'm going to show some bits of the proof of the theory that I'm going to be talking about, and then I'm going to show you my experiments with the extra neuron. So let's jump right into it, and talk about loss functions in general. So loss function is a term that you can frequently encounter in mathematical optimization, statistics, machine learning, and of course we're interested in the machine learning part. And just to be brief and to denote some things, I will be denoting the loss or cost function as C, and I'll be dealing with supervised learning, where your data set is made of n input vectors and n targets. For that, to work with it, I'm gonna denote the model that is going to be, taking the data and giving its predictions with f, and its weights will be in the brackets. So in general, if I take a data set and a model, what the loss or cost function does, it does for each point in your data set, it will give you how well, it will tell you how well your model describes the data point. So you take your prediction, compare it to the target, and the cost function will give you some value that you can interpret as being close or far away from where you want to be. From that, usually people construct empirical loss functions where they just take the average over the entire data set of the cost or loss functions. So this is how I'm going to denote it throughout the presentation. Shouldn't be too difficult, but to give a concrete example, this could be a very simple model that would have just two parameters, two weights, and this is what it would do with an input vector of some arbitrary length, right? And you could use that to find A and B so that this loss function is minimal over your data set. And this task is practiced a lot, but not too much is known about the loss functions and whether you actually can find the minima. So what you can do, for example, if I plotted here the parameter A and here the parameter B, for some data set it's not difficult to construct such a task by hand. You could find out that there is a single optimum value for A and B so that your model fits the data set as well as possible. But this is also another possible situation where you could be in a situation where you're trying to find your parameters, but the loss function over your data set for these parameters would be very complicated with many local minima. And so the optimizing methods could get stuck somewhere in between your goal and your starting point, right? So the idea comes from a paper published by Shiyu Liang. You can find it on arXiv. At the end of the presentation, I'll give the full reference to it. And so what they do is they essentially take one classifier, a binary classifier, they add a trainable exponential neuron to it, and they prove that all the local minima vanish, that all that you're left with is one global minimum, and this minimum is the same for the modified network as for the original one. So it's a very strong theoretical result, right? It really caught my attention because it's something that you think about a lot. And So I went through the paper, and yeah, I'd like to share with you my insights on the claim. The result was very surprising to me because a couple of years before that, before this year, this paper came out. If you take a neural network that consists only of one exponential neuron, so there's nothing else, you'll get exponentially many local minima. So adding something that has exponentially many local minima, in my intuition, shouldn't eliminate all the bad local minima, right? But apparently it does. So, to give more formal approach to the task that, the model works with. What they do, they don't work with arbitrary neural network. They take a binary classification task where they label their targets as -1s and 1s. This is somewhat important to the mathematics behind it, and it is quite different to what you generally encounter, right? Usually people denote these as 0s and 1s, but it's not a major change, but you need to be careful when you talk about it. And we expect our classifier to be a model. It doesn't have to be a neural network, but since you're adding neuron to its output, trainable, it's usually a good idea to take the classifier as a neural network. And you expect it to give you a single number that's going to be negative or positive, and that's how you classify the samples. So you say that your model classified your sample correctly if it gives negative output for the target -1, and vice versa for the positive number. So what the paper does as well is they take a very peculiar specific form of the loss function or of the cost function. So in general, you want to take or model the targets and calculate the loss for each sample. And they do it in a way that they take some unknown function denoted by L, and it takes a single argument, and into it they put the target multiplied by the prediction with minus in front of it, and they make some assumptions about the loss function, about the L. They're not very difficult. On the next slide, I'm going to show the intuition for it. So they expect L to be twice differentiable, non-decreasing, with all critical points being global minima, and they want all the global minima to be on the negative part of the argument. One last assumption for the model they give is that the data set is realizable with the model. So that means that there exist such parameters that the model would classify all the examples correctly. That's a quite strict assumption because in the real world data sets, you're going to have exactly the same input vectors with different targets, right? It turns out that you can get rid of this assumption if you assume this function to be convex. So it's up to you what you choose as your assumptions, but this is what we're going to work with for now. And so example of a loss function that has all these assumptions is the polynomial hinge loss. So essentially for the real number from -1 all the way to the negative infinity, it's 0. That's because in here you do the maximum, and above it, it's just a polynomial loss. This degree of the polynomial is important for the twice differentiable assumption, right? And for me, when I saw this, it was not immediately clear that this is a loss function, right? That it is going to make me classify the samples correctly. So let's take a look. I told you before that we're going to put into the argument the target multiplied by the prediction and minus inside of it. So if I have the target 1 and I predict it to be positive, or 1 exactly, or both are -1, then this product is going to be 1. With this minus, it's going to jump to the -1 where the loss is 0. And on the contrary, if you predict, if your target is -1 and you predict it to be 1, and vice versa, you're going to jump to 1 where the loss is non-zero. So this formalism works. It really forces you to classify correctly, right? So how the extra neuron works. The idea is to take the output of your previous model and really add to it output of this exponential neuron. So this could be interpreted as a skip connection, right? Because you have your model that takes the sample with some weights, right, and calculates your output. And then you take the input again, you run it through the exponential neuron, and then you add the two together. So I'm going to call this parameter A to be the scaling factor, and this is the bias, right? These weights are not going to be important for the talk, but obviously they're important for all the theoretical results, right? So another thing that you need to do to eliminate all the bad local minima is to modify the loss function, the empirical loss function. So you put in your new model. So this means the F is the sum of two outputs, but then you need to add L2 regularization for the parameter A for the scaling factor. Without this, it will not work. And I'm going to show it later on. So you do this, right? You take your original model, you add to its output the exponential neuron, you modify your loss function, and once you do that, you run your training as usual, and you're going to arrive to a global minimum. Right, is there a question? Sorry.
So what is W? Is it a matrix?
No, it's a weight vector. Just one, like, it is a matrix if you want to be strict, but it's a vector.
It's not the same as in the F0.
No, it's different. I'm sorry. I used the same letter both times. I'm sorry. Yeah, they're different parameters. Sorry, sorry for that. Right. So how does that happen? Right? How do you arrive to a global minimum? So what you do when you're doing the optimization, you're trying to find the minimum of your empirical loss function. So to find out what it is, usually you need to calculate the partial derivatives with respect to all the weights. And to show that the effect of the additional neuron vanishes in the minimum, we only need two derivatives. We need the derivative with respect to scale and to bias. So you can check real quick that if you take this, these two are really the partial derivatives that we need. And in order to find the minimum of the loss function, we're searching for the parameters A and B. You would take these equations and make them equal to 0 and try to solve the set of equations, right? And so what you can do when you get these two equations, you can multiply the second one, or the number 13, by A. Oh, sorry. This one the first one you can multiply by A and then subtract this one from the first one, and what you're going to get is the sum is going to eliminate itself, right? And what you're left with is this equation, which for lambda greater than 0 has only one solution, and that's A0. So what this shows is that if you take the modified loss function and the modified output of neural network, and you arrive to a minimum, the exponential neuron is going to be inactive, and that's the reason why the new minimum is the same as the global minimum for the unmodified model. So what we've shown here is for every critical point, the exponential neuron is inactive, right? So how about the minimum? That's the more difficult part. You need to work with some math for a while to show that it's going to be the global minimum and all the local minima vanish. But the intuition for it can be nicely seen in 1D case. So what I mean by 1D case is, let's say our model has only one parameter. Let's plot it on this axis. And in here, let's plot the loss function over the entire data set, right, for each parameter value. This would be the bad situation, right? You would get a local minimum here, but you're trying to get somewhere here where you're at the global minimum. And so what the exponential neuron does is it makes your prediction worse in the local minimum. It's trained so that it gives you, during the training, when you get to the value around the local minimum, it's going to add to your output a very large number or subtract large number, so that it changes a lot of your classifications, right? Because the classification depends on whether your output is positive or negative. So, while it's doing that, it pushes you out of the local minimum. It pushes your loss function somewhere else. And but when you take a look at the gradients, they are still very small for your original network, but they are large for the exponential neuron at that time. So your network changes very, very little when the loss function jumps, away from the local minimum. what changes is the exponential neuron. And that's the intuition behind how this idea works and why it works. Right. So I did a couple of experiments, right? Because in the paper, there are only theoretical results. They didn't take any data set, they didn't take any model, and actually add the exponential neuron to it. And I was interested in testing it in the real world. So, for this, to test this, you need to find a nice binary classifier that would be, more or less state of the art, because that's what you're interested in, right? And it turns out that it's not such an easy task. You can try and find some neural nets on published datasets because you need to be able to repeat the training, right? You can't just use results from published papers. You need to be able to rerun the training. So this is what I did, but another thing I did was, you need a binary classifier for GANs, right? You need the discriminator is a binary classifier. So I ran training of some GAN architectures on some famous data sets, and I tried to add the exponential neuron there. But I'm going to show in a couple of slides that the exponential neuron destabilizes the training. And for training GANs, you need to have a very stable optimization, right? So the generator didn't learn anything essentially with the extra neuron. That's the result of this experiment. So I'm going to focus on the first part. So I searched for nice data sets and nice models, and I was able to find a data set of EEGs. You can find it here, where a bunch of people were told to imagine that they're doing an activity that they're familiar with, or a completely new one, something they've never done before. And during that, the researchers were recording the EEG, and so this is the data set. You're giving EEG of some person, and you're supposed to guess if they're picturing doing a new activity or something that they're familiar with, right? If you're interested, go ahead and take a look. It's a nice data set. You can also find here models that they published in 2 peer-reviewed papers. Both are based on convolutional neural networks. Again, a perfect fit for this experiment, right? You can just add exponential neuron to it, try to rerun their training, and see how it goes. So that's what I did. But I ran into a couple of issues, right? It's not out of the box that you can add the exponential neuron. So if you're interested in this idea, feel free to take the snippets that I'm going to show, and we have them on our website, and use it. So the first issue is that the hinge loss in Keras is only implemented for p less than 3. So these functions are not twice differentiable if you take them with the maximum, right? So for these, the assumptions of the paper, of the whole idea, don't hold. So that's the first thing. Another thing is that you can't add a single exponential neuron in Keras. It's just not implemented. Oh, sorry. And right. I forgot the first point. Most of the Keras losses expect your targets to be zeros and ones for the binary classification task. So you need to be careful about that, because obviously it's not going to work if you miss that. So this is the first thing. You just take. I called it H accuracy, but this was the accuracy that I lost, that I wrote to see. It just compares the signs of your prediction of the ground truth with your predictions. It's not very difficult. So it's the first thing that you need to change. Then you need to write the polynomial hinge loss for greater power than 2. So for 3 I wrote it here. Really easy again, but sometimes you could get stuck on this. And the last thing is the exponential layer with a single neuron. There's a lot more code here, but what is important is that you can add the L2 regularizer, if you remember that you need to modify the loss function as well during the build phase of the layer here. And I also put this slide here to show you that the lambda that I chose for the experiment was 0.1, which is quite large if you're working with L2 regularizers, right? But it was the best one that I found. So, all of the snippets can be found here. It's a short blog post that we wrote at Rossum. Or feel free to ask me about the code. And so these are the results of the training. The blue line corresponds to the original unmodified network, and the red one is with the exponential neuron included. The blue results were quite good, right? They wrote papers about the results, so you can expect it, to be difficult to beat. But in the end, it seemed like the exponential neuron was winning. Another thing that I mentioned earlier is that you can see here the jumps in the validation accuracy, the instability in training, and I think that's why the gun experiments didn't work. But to really be sure, I ran the training multiple times, and I made the confidence intervals of all the trainings. I think this is either 5 or 10 training runs, and 90% confidence intervals. Where again, the blue line is the original network, and the red line and the red marks are the modified network with the extra exponential neuron. And it seems like it's winning, right, in the end of the training. So again, to be more confident in that, I did a statistical man-Whitney test on the maximum accuracies achieved, and it says that with this p-value, you can say that the extra additional neuron helped. So you can also ask how much it helps. It helps by like 1% in accuracy. So that's not a huge difference, right? But again, the original model was state-of-the-art, published. So improving it even a little bit is kind of cool, right? Doesn't do much, but at least it showed that the idea is not flawed, right? The accuracy didn't drop to like 20% or something like that. So another thing that I tried to test was, I've shown you that the scaling weight is supposed to be 0 near the minima, right? So I plotted its value during training. So in here you can see the validation loss, this is the validation accuracy, and this is the scaling weight, the A. And it should be approaching 0, it was, which is good. And why I did this was another idea, that it's not in the original paper, and I have yet to test it. It is to ask the question whether you can stop the training based on the scale weight, right? Because usually what people do is they use some sort of patience or fixed number of epochs that they know to work. But alternatively, in this case, you could wait until your scale weight approaches 0 and then stop your training. And you can see here that the validation loss doesn't improve anymore exactly in the regions where the scale weight is approaching 0. So that could be an idea for future, maybe to make an alternate stopping criterion. So, right, what I think could be a good idea to do in the future is, I found it very difficult to take all the assumptions that the authors made there and transform commonly used losses to it. Like even the mean square error. It wouldn't work because it's not, when you take hinge loss with p equal to 2, it's not twice differentiable. So that's one thing that could be done. We could work out how to generalize this nice results to more losses, and I think it's really difficult to find state-of-the-art models for binary classification like that you can compete with. Because there's just not that many, essentially. So I think it would be good to do more than binary classification tasks. And another direction would be the new stopping criterion and test it against the common methods, see how your model performs if you train it with this stopping criterion compared to, for example, the patience 4, which is used almost everywhere. Right. So that's it from me. This is the blog post where you can find the snippets, and this is the paper that I based the work on, essentially. Thank you. Thank you for your attention.
And in the case of any questions, I will just pass you the microphone here.
Great.
Okay, even two questions. One is, about the binary classifications. There is quite a lot of multi-class classification, like the classical ImageNet.
Yes.
And this multi-class, it's kind of similar to binary, so why not to use them? And the second question, it's, okay, for me it seems the technique, it's more definitive version of the trick that guys doing from fast AI, which when they just jumping learning rate from time to time.
Right, this cyclical learning rate,
yeah,
right?
To beat it out of local minima, it's more definitive, but I wouldn't say it's something completely novel.
Right, so the first question, to answer the first question, the difficulty is in writing out the Taylor polynomials essentially in the multi-class classification task. In here, since it's binary, you only need to move with your function around 0. You need to be above or below 0. But when you need to do that multiple times, it's quite difficult to write by hand the expansions. And also, like the result relies on Lagrange polynomials to classify the dataset correctly, and in that case, it's not obvious how to choose them. And so I think those are the two main obstacles that you would have to deal with if you wanted to do the multi-class classification. And the second question was about the cyclical learning rate, right? Compared to that, in here, you know that you're going to get to global minimum. The proof is analytical. You know it. You're sure that you're not going to get stuck somewhere along the way. You know that there's no better model in theory. I know that in practice, obviously you can just run the experiments and then compare the models, right? So that's it. But yeah, I know that the cyclical learning rate can get you out of the minimum as well. Yeah, it could. Yes.
Hello, I have several questions. You showed the graph where you measured the error, and you used validation set to measure the error, right?
Yes.
Why would you expect that eliminating the local minima in the error function would have any effect on validation?
I see. Right. I know that I've seen a lot of papers. I know that there are results comparing models that got stuck in some local minimum with the ones that converged to the global minimum, right? And essentially, the performance is the same on the validation test, more or less, usually, right? So the thing that should, improve your model is that you expect the samples in your training set and validation set to come from the same distribution. So when you get to global minimum on the training set, you should be in the global minimum on validation set unless you overfit, right? So that's the basic idea, but I know it doesn't have to work. I know that there are models that don't converge to the global minimum, and that just doesn't matter. Yeah.
Okay. Also, I wanted to ask: did you actually try to count the local minima in the error fitness landscape?
Right. That's quite difficult because the neural network is not that deep, but the number of parameters is very high. So finding the local minima is equivalent to training the network to the minima, right? So I would have to run it many times and hope that it converges to different local minima. So I didn't do it.
Yeah, I meant for some really small and simple case.
I tried to do it by hand. For example, on a data set, I took 5 samples in the data set or 2, and different models, regression models, tailored to binary classifications and things like that. And in there, it's not very difficult to come up with a model and data set that will have many local minima. You can essentially you can take, what I did was I took a textbook on optimization, and I took the test functions there that you're supposed to train your optimization on, and I tried to come up with a data set and model that would have the loss function as a loss function, the test function from the textbook. You can really do that. Like when you take just simple, for example, linear regression, and you're supposed to come up with a data set of 10 points, where the loss function will have multiple local minima, you can do it.
Last question. If there really were some procedure that would eliminate all the local minima from the error fitness, then the error function would become convex,
yes.
right? And optimizing a convex function is a simple task, like polynomial task. You can do it with polynomial algorithm.
Yes.
And the training the neural network is difficult task. It's NP hard or even harder.
Right.
So I think it should not be possible to do this.
Right. I see. The issue is that you can have your loss function convex, but it doesn't have to be convex with respect to the data set. That's like when you change the data set, because usually when you say that your loss function is convex, you're talking about the classification, right? About the output of the model. In that, it has to be convex. Like when you put in different inputs into the loss function, you want it to be convex in that. But what you're talking about, I think, is it being convex in the weights, in the parameters, right?
Yeah, and globally convex.
Yes, right. It's a strange result, I know. Yeah.
Thanks.
One more question.
Right.
Thank you for the talk. I wanted to ask about the guns.
Right.
Did you try just the vanilla gun, or did you try some more advanced, like Wasserstein gun?
Right.
Which should be more stable?
I didn't try the Wasserstein gun, but you know what I did? I took a GitHub repository with multiple guns implemented, and essentially I replaced the discriminator in them. And I haven't found any that this would work for. Yeah, but I did try the vanilla first. Yeah, on just MNIST.
Okay. Thank you very much for all the questions and answers. Thank you, Tonda, once again.
Yeah, thank you too.